Let's begin with the capillary beds. It is at the capillary beds that the exchange of materials between the blood and the cells occurs. Blood flow through the capillaries is called the microcirculation. Arterioles, the smallest of the arteries, feed the capillary beds. These are called the terminal arterioles. Venules drain the capillary beds. There are two functional types of capillaries: a vascular shunt, which is highlighted in the illustration. No gas exchange or the exchange of materials occurs when the blood is in the vascular shunt. A vascular shunt is merely a way to bypass that tissue. Your body is constantly redirecting blood flow to tissues that require additional nutrients and oxygen, or need to have waste products or carbon dioxide removed. The vascular shunt allows you to redirect the blood where it is needed. The second type of capillary is what is called a true capillary, and that's highlighted in yellow. It is in the true capillaries that the exchange of materials between the blood and the cells occurs. When materials leave the true capillaries, they move into the interstitial fluid which surrounds the cells, and from there into the cells. The opposite occurs when materials enter into the capillary. Precapillary sphincters, which are smooth muscles that wrap around the true capillaries at the entrance or the junction between the vascular shunts and the true capillaries. These smooth muscles, or precapillary sphincters, regulate the movement of the blood into the true capillaries. The opening and closing of these sphincters is called vasal motion. Later, we'll look at what causes these precapillary sphincters to contract, thus closing the entrance into the true capillary. Let's look at capillary exchange. The exchange of the materials between the capillary and the tissues occurs by several different mechanisms. Diffusion, which recall is a passive transport mechanism, where substances move from an area of high concentration to an area of low concentration. If a substance is hydrophobic, it can diffuse right across the plasma membrane or the endothelium of the capillary bed. If it is hydrophilic, it will diffuse using transport proteins, or diffuse through intercellular clefts. These are the spaces between the endothelial cells. Active transport involves ATP. This can occur through pinocytosis and exocytosis and will be used for larger substances. And lastly, bulk flow. This is what we're going to investigate further. As the term bulk refers, we're moving large substances in this case. Plasma and solids within that plasma can move from the capillary into the interstitial fluid, and also in the opposite direction, from the interstitial fluid into the capillary. Bulk flow occurs by filtration, and this is the movement out of the capillary into the interstitial fluid, and reabsorption, which is the opposite. This is the movement of interstitial fluid back into the capillary. Bulk flow occurs along pressure gradients. In other words, from an area of high pressure to an area of low pressure. And we're going to measure those pressures in millimeters of mercury. During filtration, since the movement is out of the capillary, the pressure is greater within the blood compared to the interstitial fluid. And during reabsorption, the opposite is true. The pressure in the interstitial fluid will be greater than the pressure in the capillary. Let's look at these pressures. First, we'll begin with hydrostatic pressure. Hydro refers to fluid, so this is the pressure that is created by the fluid. The hydrostatic pressure inside the capillary is actually the blood pressure in the capillary. We can use the abbreviation HP for hydrostatic pressure, and the subscript C stands for capillary. This pressure pushes fluid out of the capillary, and that is filtration. A second type of hydrostatic pressure is the hydrostatic pressure within the interstitial fluid. We'll use the subscript IF. This pushes the fluid in, or reabsorption. A second type of pressure is osmotic pressure or colloid pressure. This is the pressure that is created by the solids. In this case, the main solid will be the plasma proteins. The fluid will move by osmosis from an area of high water to an area of low water. If you recall from AP1, plasma proteins or solids determine how much water you have. If you look at the illustration on the right, I've drawn a capillary. The yellow circles represent the solids. Notice that in the capillary, I have more solids than in the interstitial fluid. Since I have more solids in the capillary, that means I will have less water. Water will always move from high to low by osmosis. So in this case, it will move from the interstitial fluid back into the capillary. Let's look at the two types of osmotic pressure. First, the capillary osmotic pressure, and we're going to use a subscript C here with the abbreviation OP. This is going to pull fluid in. And the interstitial osmotic pressure, or IF, which is going to push fluid out. What determines the direction of bulk flow is the pressure. Let's look at the net filtration pressure, or NFP. The net filtration pressure determines the net flow of fluid across the capillary membrane. In other words, it will determine whether filtration or reabsorption occurs. I have in bold net flow. So movement will go in both directions, but the overall main movement will be the net flow, and that will determine the overall direction. The net filtration rate is equal to the sum of the hydrostatic pressure in the capillary plus the osmotic pressure in the interstitial fluid, minus the sum of the hydrostatic pressure in the interstitial fluid plus the osmotic pressure in the capillary. When blood moves into the capillary bed, the hydrostatic pressure or blood pressure at the arterial end is about 35 millimeters of mercury. That pressure will drop, and by the time you get to the venule end of the capillary bed, the pressure will be 17 millimeters of mercury. Let's look at bulk flow at the arterial end of the capillary bed. We'll plug in the numbers. The net filtration pressure at the arterial end will equal the hydrostatic pressure in the capillary, which will be 35 millimeters of mercury, plus the osmotic pressure in the interstitial fluid. This pressure will be low due to decreased amounts of solids, specifically proteins. That sum is then subtracted from the sum of the hydrostatic pressure in the interstitial fluid, and this is close to zero, plus the osmotic pressure of the capillary. This is going to be 26 millimeters of mercury, and this will remain constant. Let's look at the venule end. We're going to use the same equation. The net filtration pressure will be equal to the hydrostatic pressure in the capillary plus the interstitial or the osmotic pressure in the interstitial fluid. Notice that the hydrostatic pressure in the capillary, the blood pressure, has dropped down to 17 millimeters of mercury. So that sum will be subtracted from the hydrostatic pressure in the interstitial fluid plus the osmotic pressure in the capillary. The net filtration pressure will be minus 8 millimeters of mercury, or negative 8, and since this is a negative number, we're going to have reabsorption occurring. What you need to take away from this is that at the arterial end, filtration occurs, and at the venual end, reabsorption occurs. About 20 liters of plasma is filtered per day. This is almost 7 times your plasma volume. So you're filtering a lot of plasma every day. And when that plasma with the solids moves into the interstitial fluid, that plasma has to go back into the capillary or your blood pressure would drop. So if you look at the venual end, you'll notice that 90% of what was filtered re-enters the capillary and becomes plasma once again. The remaining 10% is going to move into lymphatic capillaries and become lymph. That lymph then will return back to the circulatory system and become plasma once again. Notice what's occurring here is that your body fluids don't stay in one compartment. They move from compartment to compartment across membranes.